Alright, so what is nuclear fusion? Hopefully by the end of the video I can give you a basic walkthrough of how I understand, or basically what I understand nuclear fusion to be. So basically, said it twice already, you're going to become very familiar with this image. To spoil it for you, I think this is basically deuterium, this is tritium. I sometimes forget which is which. You fuse these two together, and these are specific types of hydrogen. They go boom, we get helium, a neutron, and some energy. It's basically very reminiscent or very closely related to E equals mc squared, which just focuses on energy transfer basically in a way. So I kind of want to start out basically to give everybody anybody who watches this, I hope they get some value from it. So I want to be very clear about the main thing to take away. Ultimately, fusion, which most people probably understand as fusing two things together. So take one thing, take another thing, bring it together to get a bigger thing usually. That idea of fusion is basically correct. Now, nuclear fusion is the same principle, but we are talking a very, very, very small thing and another very, 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 very small thing, and fusing that together to get a slightly less small thing. So if you only take one thing away from this video, fusion, taking things and fusing them together. I really hate when you have to define something with its own definition, like what is fast to be fast. But you need to explain what fast is though. Hopefully that makes sense. Again, one more time, just for repetition's sake. Fusion, joining things together. And again, nuclear fusion, two small things. You're going to understand later, the pure scale of this, because it's so small, it becomes really hard to do. So when I say nuclear fusion, if somebody asks you what is nuclear fusion, I would say fusing two things together, that would give you 1 mark out of 10. If you were to say fusing very, 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 very small things together, I'd say, you know what, that's 6, 7 out of 10, maybe an 8 out of 10, because you understand the actual concept behind what we're trying to do. So earlier, tritium, deuterium, I think that's right around. They're basically isotopes of hydrogen. So think of slightly heavier, slightly lighter hydrogen in a way. These two things come together one more time. You've heard it now, maybe the third time. Bring it together. They go boom. Well, we provide energy first of all. They go boom and we get some stuff. So that's a pretty simple diagram we show everybody when you start fusion. But there's a lot more in it, and I think we talk about the energy we put in our cells. This thing is really, really important, and it often gets overlooked. And hopefully by the end, you're going to see why it's so important. So you might think to yourself, hang about a second, are there not other things we can use for fusion? Why is it just D and T? Well, basically, we can use other things. It's just D and T basically give us the best bang for our buck, It just likes to fuse so well, so the rest of this stuff we can ignore. I don't care about this. It's just, we can use it under some circumstances, but it's just so much easier to use D and T because of the binding energy they have is how they naturally stick together. There's energy holding them together, and to kind of create enough energy to kind of rip them apart or make them separate, it's really, really, really tough. These two, D and T it's just so nice to do. It's just so much easier. So it's somewhere around here is why we focus on D and T. That's why this graph is so common. Now I kind of want to focus on giving you the scale of the problem now, so why it's challenging. Right now I'm making the video on a computer, laptop. Laptop is made up of loads of small parts. These small parts are usually made up of different types of metals, alloys, and composites. And sometimes I think, a composite? might be made of different alloys and different elements. I'm getting these terms a bit loosely confused because I'm not too advanced when it comes to nuclear fusion. But again, I'm just trying to hopefully explain some of the basics to you when they get more complicated as I make more videos. So we take an element, let's say silicon, which is basically sand in a way, and then we magnify it even more. What is silicon made out of? I think it can be a silicon element cut in the periodic table. Like, it is only itself. It's nothing more than itself. But what is it made up of? Well, it's made of like electrons, protons, neutrons, and various subatomic particles. And these are our pieces. Hopefully I explained it well, but for the last few minutes, just try and understand the size of the challenge, or how I've broken down something rather than the actual definitions. And I chose sand or silicon for a very specific reason, because I think it's very I think people can understand what I mean by sand or a piece of salt. I kind of want you to think that the sun will become relevant later. Foreshadowing. The sun is 1.4 trillion times bigger than a grain of sand. ChatGPT told me this, so it's probably correct. I hope so. And a grain of sand is 1 trillion times bigger than, I think, a subatomic particle. So hopefully that makes sense. Okay, this piece of sand is this much smaller than the sun. I want you to think of a piece of sand now as the sun, and the atom I'm dealing with would be a piece of sand. If that makes sense, Very, very small. And this, for me, is where the nuclear part of nuclear fusion comes into it. So rather than 10 plus 10 equals 20, I'm like 0.000000001 plus, how many zeros is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. 0.000000000 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 equals 0.12345678 9. That's probably correct, I hope so. So it's more this. Same principle, just a very different scale, and the scale is what becomes the challenge. I've said that so many times, but I really want you to understand that. Fuse two things together, scale. So, we have the universe just existing. I don't know why it exists. I don't know how it was made, but we just know it exists, okay? It's just here. And we've sort of kind of gleaned or worked out certain rules, and we are led to believe these rules probably hold because there's consistency in them. So, when it comes to these subatomic particles, in the sense of magnets, I'm hoping you're familiar with magnets. When you have opposite poles, they just attract and snap together. This pen is magnetic to my my tablet. But if the same poles are put together, they kind of repel. So imagine North Pole, South Pole locked together. Imagine North Pole. Well, if you push them together, they'll push apart. But imagine we take you know what? I could have got a magnet, but these two will do. So North Pole, South Pole, they come together, boom, hit together. Now, North Pole, you bring them together and they kind of push away from each other. But if I use my force, my strength, to hold them together, right now I'm transferring energy from my muscles, I guess, to keep them together. If I were to smash them into each other hard enough, they will kind of fuse and become something different in this example, but they'll kind of just be stuck together now. So that is kind of one of the principles to talk about now. So imagine I'm drawing a person holding the two magnets together. Gonna give some muscle. I'm not the best drawer, but yeah, it goes. He's using his force now. I'm going to say F equals MA to hold these things together. Again, force is where it will become honestly, once you get to the end, it's going to all hopefully make sense. I'm giving you just the small pieces together to put together, like the Lego pieces, and we're going to build something at the end. So earlier I said the universe just exists. I'm not going to get into metaphysical debates. It just exists, okay? And the reason we know this is because we test experiments and we've done them continuously. And then we've kind of built a set of frameworks and rules. And across 10,000 or so years, we've come up with theories. So he might say, oh, 1 plus 1 equals 10. This person might say, you know what? Worst person to pick. Actually, 1 plus 1 equals 2. And here's the proof. Then somebody might say, you know what? 1 plus 1 equals 2, but maybe you have negative numbers. Again, these are really, really, really smart scientists, but basically they've come up with very, very sophisticated ideas, Einstein and gravity, and then other people have tried to poke holes in it, and the fact that they haven't leads us to believe that while it may not be a perfect idea now, it's good enough to help us make progress, Like, we haven't built the best plane in the world, but we've built a plane that we think is reliable and can get us there. It might be tweaked later in the future, but ultimately it's a pretty good set of rules that we've kind of created now that are consistent. So, within these rules, there are 4 main forces: strong nuclear, weak nuclear, electromagnetic, and gravity. We do not care about gravity. Like, I can't create gravity on Earth. It's just impossible for me to do. So gravity, will ignore it. It's these forces that kind of operate at the very, very macroscopic level, maybe. Again, please don't be too mean to me in the comments about my definitions yet, but they'll get stronger. I think they operate at a very small level. And think of the universe earlier as a set of Lego blocks, and these are the rules to connect together. When we're talking about nuclear fusion practically, we're going to have to go to a very, very small level to get these things to work. Like really, really tiny. So hopefully now you get the scale. So you get the idea of fusion. Bang. I'm going to call it fusion. You get that. You now know scale. You remember the sound from earlier? You now know scale. You now know that there are some pieces and rules. Okay, so hopefully these 3 things, okay, this makes sense to me. We can use what we have now to build something. So, the first fusion experiment, to my recollection, kind of happened in, I think, maybe 1914? I think it was some guy called, Oliphant was testing, hydrogen atoms to see if they affect each other, and I'll talk about this paper at some point, because it's quite important. And they kind of proved the principle that we can, in a way, transform energy. Would that be correct? To mess around with energy. So the first experiment, we did these things with hydrogen. We put in energy. We got 10 out. In, let's say, 1914. Let's say another 40 years later, in 1956, after World War II, or something along those lines, people have kind of tried to make this more efficient, the first car is really old, but a brand new car is more modern, more slick, better technology. So some people try a fusion experiment, and you know what? We put in 100 energy, and we now get out 40 energy. Because we've been more efficient, we're getting more heat, we're messing with these rules and laws a bit more. So we've gone from 10 energy to 40 energy. These are not specific numbers. Again, it's just a principle. So you're thinking, actually, that's pretty cool. We've gone from 10 to 40. Yeah, like it. It's good. But here's where it gets tricky. In, let's say 2010-ish maybe, we're trying more experiments, and now we've got 280 energy out. Now, earlier, the example you saw of this is a very, very simple abstraction. It's what I would show a beginner to kind of introduce into fusion. But the thing is, the energy we put in, this is a really hard problem to realize in the real world. So, to put in 100 energy, this costs a lot of money. And we kind of need to get to more than 100 So Q is our value. We don't want Q of 0.8. We don't want Q of 0.4. We need Q to be greater than 1. So that's going to be Q greater than 1. So basically, if I put in 100 energy, I need to get at least 101. 99.9 isn't good enough. I need 100.1 at least. 99.9 at least shows we're making progress, which is good, but I really want to break this value now. So I don't think that makes enough sense to people right now. When I say fusion needs a lot of energy, think of our magic magnetic box now. We've got a isotope of, I think that's deuterium. Yeah, got it right. We have an isotope of deuterium in a little box now. It's by itself. It's just chilling there in the atmosphere because we've got homeostasis. If we heat the box now, the heat energy goes into the box now and eventually finds its way to the deuterium atom. So it's getting hotter and hotter in the environment, so it might wiggle about a little bit more, okay? And if we can put a lot of heat into this, boom, boom, boom. So imagine we've got some air here, oxygen, 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 oxygen. This oxygen molecule gets hotter and starts moving about and bouncing against the walls. And this molecule gets hotter as well. Then this one gets hotter. Then this one gets hotter. Then this one gets hotter. Then they're all moving around the magic box. And imagine the wall's very hot, so when it hits the wall, it loses a bit of heat, but it's still got more. Let's say it loses this heat. This is gone. It's still got this much energy being transferred, moving about. So as they collide, this guy gets more and more energetic. And if we can give enough heat, enough energy, we start to see some pretty interesting things. And basically, we create what we call a plasma. It's like a gas which has lost its, I think, electron. It's in this very how to put it, amorphous, weird state. And plasma is definitely something I need to explain later. But let's just ignore it for the moment. So the three things that I need the place to be really, really tight, because to heat a box up is not easy. So it needs to be really tight. I need to be able to get this little guy, this deuterium, to kind of stick in a certain place. It can't just keep bouncing everywhere. And I need really hot. I'm not saying hot like I need to boil a kettle of 100 degrees. I need it to be hotter than the sun. I want 100 million degrees. I need to heat a place up to 100 million degrees. And on Earth, where we live, that's not really easy. This guy, good planet, little bit overrated, still good planet. It's not really good at fusion. Whereas this guy, the sun, really good at fusion, really big. He is so big that he has his own gravity. This guy, no gravity, weak. And really hot at the core, not as hot at the edges, but it's got so much space that it can just create fusion. It's really good for fusion, So how do I explain the issue in terms of heat now? The best example I could think of is we're back to Earth now, and we have a volcano, which technically speaking would be powered by gravity, because gravity moves the Earth, and the Earth moves the plates, and the plates create energy. Doesn't matter. We have a volcano. It's about to erupt. So in the chamber, the magma at point number 1 is the hottest. But the thing is, at point 1, the heat is dispersing. So you can see now here, between the crust and the lava, heat from the lava is slowly being transferred to the crust. So this volcano is losing heat very, 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 very slowly, but it's losing heat. Everything here is not one single thing. It's millions of things together interacting. So the volcano explodes. And we have lava flowing out Now, if you're familiar, you often see like lava flowing out on the street and it becomes very hard very quickly. That's because this guy now is not surrounded by really hot magma. Lava, yeah. It's surrounded by air, the ambient temperature of air. And this, let's say 100 degrees. I mean, let's say 600 degrees as a number. This 600 degree lava is surrounded by 100 degrees, no, let's say 40 degree oxygen. So the heat is going from here, being transferred into here. So the air around it's getting hotter, and this thing's becoming colder. And eventually it kind of reaches homeostasis or balance, or there's probably a term, but I'm not there yet. That's kind of the principle. Hopefully now, this can help us make sense in our magic box. So, the magic box. Hey, look at this magic box. First of all, I need to get to 100 million degrees. And you might be like, okay, how do you do that? Because 100 million degrees is crazy. It's hotter than the sun. Yeah, exactly. It's really tough. So, let's say we get some really powerful lasers. Laser. Boom. I could change colors, but my tablet's not been working well. So, let's say we get a laser, or like a magnifying glass. A magnifying glass, perfect. Great analogy. And we just like shine heat on it. Boom, 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 boom. Boom, 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 boom. So, gradually, the box gets hotter and hotter and hotter and hotter. If we can turn enough energy from here into there, this energy will transfer into the box. So, we stick our deuterium and tritium in the box. We now heat the box up really, really hot. As the box gets hotter, these guys bounce over more and more and more. Like, they're bouncing really excitedly. Is that a word? Like, they're like, okay, so it's like boom, boom, boom. The hotter it gets, the more it moves. It might bounce off each other, bounce off each other. If it moves fast enough and hits each other, bang. That's kind of where fusion comes into play now. But to be honest with you, the only metal on Earth, I think, with the highest melting point is tungsten. And it can survive 3,000 degrees, basically, before like melting. So, you see these numbers? They don't really work. We essentially need to find a way, I think using magnets really, or lasers, to heat a very small part of it really hot really quickly and make sure these guys moving about, they move in certain ways. I can't have them move left, right, up, down randomly. I need them to move into a certain path that I decide. And that's like magnets in a way to talk about later, but that's kind of not in the scope of this video right now. So, what does this mean? So why is this hard? Like, you occasionally hear fusion is 30 years away, 30 years away. Well, to build the magic box, it's really hard. It's really expensive. Like, each part here is so hard to manufacture. Like, there aren't that many magnet manufacturers in the world, and these manufacturers, they're busy building other stuff. So, ITER, pretty cool, and Spark. Spark cost about £1 billion, maybe $2 billion, and I think it took like less than 10 years, because this is to scale. Whereas ITER took, I don't know, like 20 years, and is estimated between 20 and 45 billion pounds. That's not a good number, is it? So, let's take each part of this. Like, you don't just go to your local shop and say, oh, can I get like a magnet, please? You have to put in an order of a very, very specialized part, and each part takes like tens of 20s of years to kind of do it. And I think there was a part called a gyrotron now, which I think uses radio frequency waves to heat up the part of the magic box. And like, I think only 5 places in the world make gyrotrons or something along those lines. Or basically, I think like only 100 get like made a year, and we need like way more than that. So it's not easy to build. And also one of those places is Russia, and the rest of the world's not playing well with Russia right now. So really hard parts to build. And when I mentioned earlier, well, I need, let's say ITER's somewhere around 90, maybe 100. There aren't that many places in the world that can throw 45 billion pounds of spare cash out there. That's why it's really hard to do, you know. Even even Spark, like, you don't think 1 billion is a lot of money. That's 10, 100,000, 10,000, 100,000, million, 10 million, 100 million, billion. There aren't that many people with this kind of money. And these kind of people with money would rather probably invest in something which pays them guaranteed money. Like if I tell you, hey, give me £1 million for something that might or might not work and might help us get to energy in like 30 years, I'd be like, please, not going to work. Like, only governments at scale can really build the devices necessary to do this. You can build smaller devices, but I think unfortunately for like complex geopolitical reasons, we kind of need fusion to work in the next like I think we've hit peak oil, or we'll hit peak oil at 2050s. Renewables are pretty good, but we kind of want fusion to work because fusion's pretty safe compared to everything else. Like, fusion is the holy grail. We put in 100, get 101. And honestly, there's so much fuel for fusion. Like deuterium is, you can just make it from seawater with some electricity. Boom. Tritium, not so much, but fusion's pretty good for these reasons. So we need this quickly. You know, the UK government's investing in something called STEP, the spherical tokamak for energy production. It's used more to regenerate the area, but we want it to work. And we're talking like a couple of billion here and there, you know, to build this. Like, the UK government does not have billions of pounds to throw on projects. Okay, the UK government is running out of opportunity to throw billions of pounds at projects because they kind of need these projects to return on the investment soon. Otherwise, they run out of money, and that's not good. And yes, we are 3 trillion in debt. But like billions of pounds, it's very hard to find, seeing as we run a deficit. So we spend more than we make. So asking us to spend £1 billion more is pretty tough if we don't get like results. So that's kind of why fusion is so hard to do. So hopefully you understand what nuclear fusion is. You can stop the video and make a comment or just work out for yourselves. We fuse two things together. Hopefully you now understand the real world physics and challenges of fusion. Like, we want to create a magic box, we want to make the magic box hot enough, we want to put certain things in the box, and then these things should fuse. And hopefully you understand like the basics of the real world part of fusion. I don't think I explained it in enough detail, but like, just understand you're asking to create like a very, very specialized, okay, you go to McDonald's and you say, get me some chips. McDonald's like, you know what? Cool. We'll get you some chips right now in like 10 seconds. We then go to McDonald's and say, you know what? I want some chips, but I want no salt. Like, you know what? Okay. No salt. Give us like 5 minutes. In the next batch of chips, we'll put no salt for you. And I'm like, cool. Maybe 5 minutes. Okay. You now go to McDonald's. Okay, can I get a burger? But can I get a burger with specialized sesame seeds grown in a very small region in Japan on a mountain? So I want those seeds to be there. Can I get like the best beef in the world from like another place in, let's say, Australia? Some Wagyu beef, Australia. Can I also get some cheese? But can you like give me like 12-year-old, really old cheese, you know? That's like out there in the world somewhere. Okay. And you're like, okay, no, also, when I get my drink now, can I have like fresh lemonade that's like really, really like fresh as in you literally made the bubbles right now? And then they're going to turn around and look at me like, what are you asking for? Well, that's kind of what I'm asking for, like a very, very, very bespoke part that most people just don't have. So that's why it's so tough to find it. And I was going to do a fun video for me, but maybe later. Maybe that's next video, like 10 questions. So, a bit of a long, rambly video, and I did kind of not give, I'd say, appropriate detail about subatomic particles, but I'm kind of improving on that. But I really do hope you got the basics of fusion down, and first of many videos, so yeah.